All right, well, welcome everybody. I think this is working. Welcome. All right, well, today's the last day of class. I hope all of you finished your final exams successfully. Graduation tomorrow. I hope we have some good some graduates in the room. Is anyone graduating tomorrow? No? Oh, no, maybe another couple of years. Well, welcome. You're here. This is the First Friday Astronomy event. For those of you who've never attended before, my name is Brian Jackson. I'm a professor in physics here, Boise State. I'm an astronomer. Again, for those of you who have never attended one of these events, this is a monthly lecture series. It takes place on the first Friday of every month, 7:30 p.m. Mountain Time. In this room, we'll be in this room all for the foreseeable future. And so if it's a first Friday of the month, this event is taking place that evening, all throughout the year, even if we're on summer break, which we are starting tomorrow. We'll be having this event. And so we've got a really great lineup of speakers for this summer season. Starting tonight, you'll see the first of those. So again, always welcome to join us. They'll be in person, but in case you can't attend in person, you can visit boi.st/astrobroncos live, or you can grab a photo of this QR code, and that'll take you to the YouTube live stream where this is actually being live streamed right now. There's also an archive of previous talks going back, I think, 2 years. So if there's a talk that you want to see that you didn't manage to catch, it's probably on YouTube there. This is a donation supported program. So the state is not paying for it, the university, it's you guys are paying for this. And so if this is the kind of programming that you like and you enjoy, feel free to visit boi.st/astro-give. And I think these capital letters are critical, but you can also grab this QR code and it'll take you to the donation page where you can help support this program. So we could not do this without your support. So thank you very much. I'm afraid you noticed the clouds on the way in tonight, so we're not going to be able to do any stargazing, but we do have a really exciting, beautiful astronomy mural to unveil tonight. So if you stick around, you're welcome to go up to the observatory and we'll show you this brand new mural designed and created by our students. So we'll do a little unveiling this evening. So if that's something you're interested in, stick around in the lobby after the talk and we'll take you up to see that new mural. It's amazing. So, okay. With that, I want to introduce our speaker, Professor Catherine Neish. Fun facts about Professor Catherine Neish. She's a big Battlestar Galactica fan. Any Battlestar fans? Awesome. You're in good company. Catherine and I, yeah, well, maybe. Catherine and I almost died on Mount Whitney. Severely injured. No, it was a fun hike. And I have two facts or two truths and a lie, and she's asked me to relay these two, and you try to guess which one's the lie by the end. Okay, so Catherine lived with an astronaut while she was in high school, has visited Antarctica, and was in roller derby. So one of those three things is not true. So think about that as you're listening to this talk. And with that, I'm going to switch over to Catherine's talk, and let's give her a round of applause to welcome her. How do I unpin this? Oh, there it is. Remove pin. I'm going to do this one right here. Well, there you go. I think that's got it. Would you check? Are you on the live stream right now? Caitlin, would you check and see if we're... I don't seem to be able to pin it, but maybe that's fine. Yeah, sorry. Switch this. It's the other pocket.
This dress has pockets. Cannot recommend that enough. Yeah. Okay, can you hear me? Is the mic on? Yeah, okay, great. Good evening, everyone. As Brian mentioned, my name is Catherine Neish. I am an associate professor at the University of Western Ontario, which is located in London, Ontario, the second best London in the world. Can we dim the lights here at all at the front? Thanks, Caitlin. And I'm here to tell you about a mission that I'm involved with called Dragonfly, which is the fourth New Frontiers mission to be flown by NASA. And this is something I've been working towards my whole career, and I'm really excited to see it take shape. So this is a picture of my favorite place in the solar system. And I imagine you're all wowed by this beautiful picture of Saturn. You can see the storm clouds. You can see the edge-on rings casting a shadow onto the planet here. But I'm not talking about Saturn. I'm talking about this rather nondescript orangish blob that sort of is floating here in front of Saturn. And that is Titan, which is the largest moon of Saturn. Second largest moon in the entire solar system. If it didn't orbit Saturn, we would probably call it a planet. And the thing that really sets Titan apart is its atmosphere. So here we have this gallery of moons throughout the solar system, Ganymede being the largest, Titan right behind it, Callisto, Io. Anyone recognize this one? This one might be familiar. That's our moon, Europa, and so forth. But really, you'll notice that Titan is really different from all these other moons. You're not seeing its surface here. You're seeing its hazy, organic-rich atmosphere. It's one of the few places in the solar system with a thick atmosphere. The only other one, other than Earth, that is predominantly nitrogen. So really, Titan is quite weirdly Earth-like in its strange way. We've had two opportunities to visit Titan and explore it in detail. The first being the year before I was born, the Voyager spacecraft visited Titan. But when it visited Titan, we knew so little about it that there was not a single instrument on board that could see the surface. And so we learned a lot about Titan's atmosphere, which is quite incredible in its own right. But we learned basically nothing about its surface. However, in the intervening years, the 24 years between Voyager 1 and the Cassini mission, we were able to develop instruments and design them so that we would finally be able to see the surface of Titan. So it wasn't until 2004, when I started grad school, that we were first able to see the surface of Titan. I don't think we could say that for any other place in the solar system. So it was this mysterious place that we finally got to see just 20 years ago. And I was hooked. I showed up in Tucson, Arizona, in the summer of 2004, started seeing images from Titan, and I wanted to learn more. And we continued to learn more for the next 13 years before Cassini sadly ended its life by plunging into Saturn in September of 2017. This little guy here, attached to Cassini, is the Huygens probe. That descended through Titan's atmosphere and eventually landed on the surface in January of 2005. That gave us our only really high resolution views of Titan. And we're hoping with Dragonfly that we can get many, many more views like the ones that Huygens provided us. So to give you some perspective, this is what we knew about Titan before Cassini. This is a picture from Voyager. For 25 years, this is what we knew about Titan. It was orange. And the orange is due to the fact that it has a lot of organic molecules in its atmosphere. So I said it's primarily nitrogen, but there's also a little bit of methane. And those two molecules react to form this really hazy orange gunk, like LA on a really bad day. But we couldn't see through all that haze until Cassini. And Titan really transformed from this, sort of featureless orange blob into, a whole world. So this is an image from the visual and infrared mapping spectrometer on Cassini. So this is showing Titan in false color in infrared wavelengths. And we started to see things that I don't think anyone predicted. There's a whole equator, and I'll show you close-up pictures of these. It's just covered in sand dunes. There are impact craters. There are mountains. You can't see them in this picture, but I'll show you a picture later. There are seas of liquid methane near the poles. And this is all on a planet that's 95 Kelvin. That's 200 degrees below the freezing point of water. It's freezing. Water ice is the bedrock on Titan. It is very, very cold, and yet weirdly Earth-like at the same time. So how is it Earth-like? Well, we see storms. These white features here, these are clouds. And these clouds actually rained. The surface darkened after these clouds passed and then brightened again, just like a rainstorm we saw earlier tonight here in Boise. And so we've seen many clouds, but these clouds are not made of water. These are methane clouds, raining methane liquid drops onto the surface of Titan. And what do those storms do? Well, they produce streams and rivers. So this is an image taken by the Huygens probe as it was descending through Titan's atmosphere. You see here rivers, dried out river valleys, much like you might see looking out the airplane window on a trip from Boise to California. So it is very, very Earth-like in many, many ways. And then those streams feed into lakes and seas of liquid methane. So this is a radar image of Titan's North Pole. There's the North Pole. And we have 3 large seas, Kraken Mare, Ligeia Mare, Punja Mare. These are the size of the Great Lakes. These are substantial bodies of liquid. They're just not water, they're methane. And we know they're liquid because they're so smooth. So in radar, if you see a black patch, that means it's very, very smooth. And when you see a bright patch, it means it's rougher. So all these dark patches are liquids. This is just noise. That's why it looks funny. And we know they're literally flatter than a pancake. And we know that because this is an infrared image. And what we're seeing here is a glint off of one of those seas. So just like, again, pretend you're in that airplane flying from Boise to California. You look out the window at sunset, there's that glint off the river into your eye. This is called a specular reflection. You only get this off extremely smooth surfaces. So we know that these lakes are smooth at the micron level. They're so flat. And so, they must be liquid. So that was the poles. Let's return to the equator. And what we see here are just line upon line of sand dunes. So all of these lines are sand dunes that go on for thousands of kilometers, marching parallel to one another. But this is not the sort of sand you find on your summer vacation to Florida. This sand is made out of organic gunk, we think. This is something we're going to test with Dragonfly. So I like to call this carcinogenic sand. It's not the sort of sand you'd want to play around with on your holiday. But what makes it sand is the size. It's the right size to be picked up by the wind and blown into these sand dunes. So here it just happens to be made of a different material than we find on Earth. There may be volcanoes on Titan, but think about it. Its crust is made of water ice, right? What happens when you put an ice cube in a glass of water? It floats, right? On Titan, the lava would be water. So how do you get the water to, rise up and overtop the ice cube? We don't really know, but this feature sure looks like a volcano with a lava flow coming out of it. So, there's a caldera here, there's a mountain here, maybe a lava flow. I don't know how to explain this other than a volcano, but I also don't know how you get volcanism on a planet made out of ice. So it's a bit of a conundrum here and something people are still actively studying. Another place you can get liquid water on the surface of Titan is in an impact crater. And this is actually what I primarily study, are features like this. This is Sinlap crater, probably the freshest crater on Titan. All the craters on Titan are named after gods and goddesses of wisdom. The largest crater on Titan is named Minerva, the Roman god of war and wisdom. And so here, a large comet struck the surface not too long ago, made a big hole in the ground. If you've ever been to Meteor Crater in Arizona, same process. And what likely happened is it also melted the surface as it impacted. And when you melt a surface made of water ice, now you have water. I mentioned that Titan has a lot of organic molecules in its atmosphere. So now we've got a really interesting place to study. You've got water, you've got organic molecules, maybe you have the origin of life. And so this is what we want to study with Dragonfly. Oopsie. So what we've learned from Cassini-Huygens is that Titan is this incredible ocean world with an organic rich atmosphere. And so if you want to understand the processes led to the origin of life on Earth, we can use Titan as a natural laboratory to study that. I forgot to mention that Titan also likely has an interior ocean of water. 15 times the size of Earth's ocean, buried maybe 100 kilometers below its icy surface. So perhaps this is another habitat where we could potentially have life. Okay, so here's Titan again. Let's review the basics. Its atmosphere is made of methane and nitrogen. This gets bombarded with ultraviolet light from the sun, charged particles coming from Saturn, and all sorts of interesting chemistry happens. And we start making more complex organic molecules. From the simplest, which is ethane, which is also a liquid on the surface, to very, very complex molecules. And Cassini found evidence for molecules as large and complex as a protein. Like these are huge organic molecules that are just sitting there in Titan's atmosphere, and then eventually we think settle to the surface where they can interact with possibly these liquid water reservoirs that I was mentioning. So really, Titan has all the ingredients needed for life. So I don't know who voted with Mars or Titan, which was the most likely to have life, but you know, I hope some of you put your money on Titan here. We've got energy from the sun. We've got solvents. We've got both methane and liquid water. And we've got most of the essential elements for life. I don't know if anyone's heard of the schnapps, where we need carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur for all life on Earth. Titan likely has schno. We're not sure there's much phosphorus or sulfur there, but certainly you can do a lot of interesting chemistry with just these 4 elements. So if life is not on Titan, I think at least the steps towards life are present there. And actually, this was the basis of my PhD thesis at the University of Arizona. So here are the solvents that we know about on Titan. We have these lakes of liquid methane and ethane near the poles. This would be weird life. This would be life that we have never seen before. We do not understand. I'm not convinced it exists. It's very cold. I'm not sure how you get life occurring, you know, at 200 degrees below the freezing point of water. That's very cold. Things happen very slowly. This is not life we understand. So I'm more interested in these scenarios, the lava flows and the impact melts, where we can get liquid water on the surface mixing with those organics, because that would start to make life as we know it, which we can better study. And so this is what I did for my PhD. I made these haze analogues, so trying to recreate the haze particles that are formed in Titan's atmosphere. We call them tholins, which was a term coined by Carl Sagan, who also studied these, after the Greek word for muddy, because they look kind of like muddy. Unfortunately, they're also carcinogenic and may have actually led to the cancer that killed Carl Sagan. So I was very, very careful when I worked with these. I dunked them in water and I left them there for not that long, hours, days. And when I analyzed the results, I found amino acids like glycine were present. So these are the building blocks of proteins. This is the first step towards life. So just give you some behind the scenes, some of the results of these studies, see how we do this sort of work. This is a liquid chromatography mass spectrometer. So what we did is fed it some standards. So we know that we were giving it these 3 amino acids. Glycine's the simplest, alanine's the next simplest, serine is the third simplest. So these are standards that you can buy at any chemical store. And then we compared it to the molecules we got from our Titan experiments. And if I flip back and forth, you can see that they overlap very well. So this confirms that simply by mixing Titan organics and water, we could make amino acids. So easy as pie. These reactions were taking place over the matter here you can see is hours to days. That's how fast they happen. So we've got the ingredients, we have the time to do it. I'm convinced there are amino acids on Titan. And this is what I said on the last page of my dissertation, which I'm going to zoom in now to show you what I said there. So I was optimistic. This is December of 2008. I was graduating, and I was excited that we were going to have a new flagship mission to Titan to get new insight into these processes I was telling you about. And I ended it with this line: Titan has been conducting natural experiments in prebiotic chemistry for eons. Now all that remains is to collect the results. So I was really eager to go back and see if these experiments I'd done in the lab were correct, and we would find amino acids on Titan. So, graduating with a sense of optimism. And just to give you some context before I go into the next part, NASA has 3 levels of missions. So the one I mentioned in my dissertation there is the flagship. These are very expensive, billions of dollars. Cassini was a flagship. Mars Perseverance, which is currently roving around Mars, that's a flagship. Very expensive missions that are directed by NASA. So you can't say, I want to do this mission. NASA has to tell you to do the mission. The next level is New Frontiers. So these are mid-tier, so only $1 billion, chump change. And there's a list of a couple of different options that you can propose to NASA to do one of these missions. So we've had 3 that have flown. New Horizons, anyone know where that went? Quick quiz, yeah. Oh, so the first New Frontiers mission was called New Horizons. Does anyone know where that one went? Pluto, yeah. So that gave us our first views of Pluto. The second one was called Juno. Anyone know where that one went? Jupiter, yep. Third one, Osiris Rex. That one is actually coming back home here any day now. That went to an asteroid and is currently bringing a sample back. And as you'll learn, Dragonfly is actually the 4th New Frontiers mission. And then we have Discovery, and these are cheap missions, only $500 million. And people can propose any mission that they like. So, but if you want to get into one of these 2 categories, categories 1 or 2, you have to be guided by the recommendations of the planetary science community. And honestly, to get to Titan, you probably need at least $1 billion. You cannot do it for this amount of money, unfortunately. So the decadal survey came out in 2013 called Vision and Voyages. And here is what it recommended. So what we're seeing here are the recommendations for the flagship missions, and then the recommendations for the New Frontiers missions. Well, what do we find? They recommended a Europa orbiter, which is actually launching, I think, next year, called Europa Clipper. So that's happening. Titan was number 2, unlikely to get funded. NASA can only give out so many billions of dollars. And then when you look at the New Frontiers, you probably can't read this, but Titan was not on the list. There was one Comet Sample Return, Venus In Situ Explorer, South Pole Aiken Basin, like all these different options, but no Titan. And then, like I said, Discovery, we probably wouldn't have enough money to do a Titan mission on a Discovery budget. So now it's 2013. Now my optimism is quickly dwindling. I'm not going back to Titan in my lifetime. I better go study something else. And actually, I now study the moon as well. So if you have any lunar geology questions, hit me up. But then something unexpected happens. This is an email that landed in my inbox in, let's see, I think it was January 6, 2016. And out of nowhere, they had this announcement for the next New Frontiers mission. Out of nowhere, this line, Ocean Worlds, Titan and Enceladus shows up. This was not supposed to be there. 3 years ago, that was not on the list. To this day, I do not know how it ended up on the list, but boy, am I glad that it did. Because this now allowed us to propose a mission where we could go back to Titan and search for those amino acids I was so excited to find. And so that's what we did. Some colleagues of mine put together a proposal, and we went ahead with it. So 2 colleagues of mine, one of whom is a professor at the University of Idaho. The other was my first PhD advisor, came up with this idea called Dragonfly. So these people had both been thinking about aerial missions we could send to Titan. And drones were really becoming quite a hot commodity around that time. And they're like, well, why don't we send a drone to Titan? Now you're thinking to yourself, well, shoot, why not send a rover, right? Why are we going to send a drone to Titan? And that is because Titan is one of the best places to fly in the solar system, better even than Earth. So if anyone here likes XKCD, this is a fun read. It's called Interplanetary Cessna. And so they have a little article telling you what would happen if you tried to fly a Cessna on all these different planets. I like on Venus, it's like slowly disintegrating in the acidic rain here. Mars, it would crash. I'm honestly quite surprised that the Ingenuity helicopter has worked as well as it did. Mars is a terrible place to fly. It does not have a thick atmosphere. But Titan is actually probably the best one. And here I'm just going to quote what they say in this article. And so we've saved the best for last. When it comes to flying, Titan might be better than Earth. Its atmosphere is thick, but its gravity is light, giving it a surface pressure only 50% higher than Earth's, with air 4 times as dense. Its gravity, lower than that of the moon, means that flying is easy. Our Cessna could get into the air under pedal power. So why rove on Titan when you can fly? And honestly, we know so little about Titan. We could get stuck in a puddle. We could get stuck in the mud, right? Let's just fly out of that situation. And even Mars rovers, and Mars is objectively a much better place to rove, have gotten stuck in the sand. So let's just avoid all that and fly instead. So came the Dragonfly concept. And this really gives us an opportunity to see a lot of Titan very quickly. In one hop of Dragonfly, we can go as far as the Opportunity rover went on Mars in a decade. So we can traverse quite large distances by using this aerial capacity. So we put the proposal in 2017. It was down selected in December of that year. We got another year to further develop our mission. We were competing against a comet sample return mission called Caesar. And then in 2019, I was sitting outside in my backyard. I think Penny was there, my daughter, who's in the back of the audience. I was holding my baby son, Jack, and I got the call that our mission had been selected, and I was pretty overwhelmed. Yes, my son had just been born a few months prior, so it was a good year. It was a good year. Now, our current launch, this is, I don't know if some of you have seen the news, Congress just stole some of our budget. So this is a question mark here. There's been a lot of controversy with this. If you've heard of Mars sample return, that has been taking a lot of budget from other missions. So it's really put some of these dates into question. But we're still hoping to arrive at Titan in the mid 2030s, so about 10 years from now. This is Dr. Elizabeth Turtle, also known as Zibby, on the day of our selection, standing next to a 1/4 model of Dragonfly. And she's been an excellent leader. It's really a great team to work with. And you don't realize just like how many people are involved in a mission. This is just a fraction of the people who have been involved in Dragonfly. It really takes a village to make one of these missions fly, but I'm really so fortunate to work with this really exceptional team. It's been one of the best experiences I've had. So let me give you a little bit of a glimpse of what we're hoping to see when Dragonfly lands on Titan in 10 years. So I'll kind of narrate it as it goes along. This is going to be a video. All right, so here we are. We're at the edge of the atmosphere, starting to descend in our heat shell here. Titan has quite a thick, distended atmosphere. So it's actually a pretty easy place to land, a nice cushion on your way down. So on Mars, you might have heard of the 7 minutes of terror as you're trying to get through that really thin atmosphere without crashing. My colleagues call this entry into Titan 2 hours of moderate concern. So it really should be a pretty easy landing. And we're going to come right out the bottom. So the bottom of the heat shield falls out. And we're literally going to fly to the surface right out of the gate. I don't think any other mission has done this. And we'll have our first powered flight and our first landing here on the surface. We're going to do a little bit of reconnaissance to make sure we're landing in a safe place. We've also picked a landing site that we think should be pretty benign, and then set down. And you can see then we're going to deploy our high gain antenna. This is how we talk to the Earth. Oh, I guess that didn't happen. It's right here. It's tucked away. It'll come up and transmit to the Earth. You can also see this is our power source in the back. This is a radioisotope, so we've got a nuclear generator on board. That's going to power a battery, and the battery is what lets us fly. We're actually an octocopter, got 8 wings, 1, 2, 3, 4, and then 4 on the other side. You can see the cameras here. We're going to be looking at the surface. We've got a drill down here to collect samples. And this is really large. This is about the size of a small car. We have this fantastic VR Dragonfly at APL where the mission is being run. And I once measured it. It's about as tall as me. And if I lay down, it's about twice as long as me. So it's quite a large spacecraft. Where are we landing? Well, earlier I told you about the importance of impact craters for prebiotic chemistry on Titan. So we're planning to land near an impact crater so we can sample some of these materials, find these amino acids. So this is our target. It's called Selk crater. It's one of the fresher craters on Titan. And we're landing in what we think is a pretty safe spot. So it's just south of Selk crater is one of those large sand seas I was telling you about. And we think this is a pretty safe place to land. Here's an analog on Earth, a sand dune area. They have these interdunes, which are really flat, no large rocks to get in our way. So we think this should be a pretty safe bet for a landing site. And then we can slowly hop our way up to Selk to look at those products of prebiotic chemistry that we're looking for. The Dragonfly engineers are hard at work to test out our operations. So we have done some work in sand dunes on Earth. So this is a video showing you how that has happened in the past. I think this happened last year. So this was done in California, the Imperial Dunes. That's also where they filmed Star Wars, I think. Anyone correct me if I'm wrong. And so they were doing a field test and what we think a place like our landing site is going to look like. So they took this test model out. Size model. It's definitely Dragonfly itself will be a lot bigger than this. I love that it has its own like tail markers, like a real airplane. I think there's another shot where you can see it says experimental aircraft. But it's got, all the official signals that you need, signs. And here they are launching it into the sky. There we go, experimental with its call sign there. This, unfortunately, is a shot we will never get on Titan because we're only sending 1 drone, not 2. So we'll never get a picture of Dragonfly flying. But we might get a picture like this where you can see the shadow there on the ground underneath it. And this is probably representative of what we're going to see on Titan. The lighting there is quite low. It's always basically dawn or dusk. Probably won't see any dune buggies. If so, that's going to be a nature paper for sure. But otherwise, I think this is a pretty good analog to the sorts of sites we're going to see on Titan. Just beautiful. I can't wait to see these pictures coming back from Titan in 10 years. Yep. So now it's about to land, and you'll notice as it lands, it's going to like kick up some sand. I think they show that. Yeah, you can kind of see how it's kind of kicking up the sand there. Not so much because it landed on the pavement, but those are experiments we're hoping to do on Titan too, where we're going to like purposely land it to kick up sand to see how well it moves, given different velocities of wind. So lots of cool science to do with Dragonfly. This is a kind of a schematic showing you what the spacecraft looks like and what the different instruments are. It's changed a little bit. We're constantly refining things. These cameras no longer exist. But as we move towards the final design. But the basics are we have 4 main instruments. DragMet, which is a fun name, is our meteorology package. So it's going to be our weather station on Titan. It also has a geophone to look for any seismic signals from Titan, which I think is pretty fun. The real workhorse of the mission, though, is DRAMS. This is a mass spectrometer. This is the one that will tell us if there are amino acids on Titan or not. And it's hooked up to this Draco sampling system, which is now just one drill, which is going to drill the surface, suck up the stuff, and spit it into the mass spectrometer. It's basically a big vacuum. And the only reason we can do that is because Titan has such a thick atmosphere. So you couldn't have a vacuum on the moon, but it's easy to set that up on Titan because of its atmosphere. We have a bunch of cameras all over the place. Some are looking at the ground, some are looking at the horizon. I think we have a microscopic imager. So we're going to get lots of the different views of the surface. And then we have a gamma ray neutron spectrometer, which is a way of telling what the surface composition is. So you spit out gamma rays and neutrons. They bounce off all the components of the surface and the subsurface and give you characteristic signals if it's carbon or nitrogen or oxygen, whatever the case may be. What's cool though is we're bringing our own neutron gun essentially, because unlike other planets where these things, gamma rays just naturally come from space, Titan's atmosphere shields those out. So we partnered actually with a mining company called Schlumberger, who do this when they drill down into the Earth's crust to look for oil. And they have these gamma ray neutron spectrometers that they use. So we're partnering with them and we're going to use one of their spectrometers to study the composition of Titan. We'll probably find oil there too, spoiler alert. So let's just give you a little idea of sort of the results we're going to get from the different instruments. There's an instrument very similar to DRAMS on Curiosity, which is one of the Mars rovers. And they were able to detect organic molecules like benzene here on the surface of Mars. And we're hoping to have similar results with DRAMS. Dragons, I mentioned, is that gamma ray neutron spectrometer. So we blast those neutrons into the ground, they bounce around, come back out, and we get spectra like this that tell us what the composition of the surface is. So is it ice? Is it organic? This is what we're going to be able to tell with dragons, which is also a really great name. I know my daughter is a big fan of dragons, so this will be her favorite. It is spelled wrong, yes. DragMet, well, like I said, it's a meteorology package, but what I'm really interested in is the fact that we'll be able to detect Titan quakes on the surface to study any interior activity, maybe hopefully get a sense for the thickness of Titan's ice crust and where that ocean below might be. And then DragonCam will give us all these beautiful images to study the geology of Titan's surface. Not dissimilar to these pictures of Mars here from, I think, Curiosity. So we'll get very similar images. We even have a LED for night imaging, which is fun. Titan's day is 16 days long, so we're going to have 8 days of light and then 8 days of dark. But that gives us some time to, study the results and prepare for the next day. So it's good that it has a slow rotation. So oh gosh, I have no audio. I'm just going to have to narrate this for you, I guess. But this is a quick video kind of summarizing the science that we're going to get for Dragonfly. If you want to hear the audio, you can find it on the Dragonfly website, but I will just attempt to narrate it for you. Okay. So here's Titan going down into its atmosphere. All right, here you've seen this already. But it's going to show you a little bit more detail about how some of the instruments are going to work once we get down to the surface. Here you can see it kicking up sand. All right, so now we see the Draco system. Oh no, sorry, we're doing the gamma ray right now. So they're pulsing to get information about the composition of the surface. Is there nitrogen? Is it carbon rich? What is it made out of? Is there layering? How deep is this water ice layer under the organics? Okay, and here's the cool part. This is Draco drilling into the surface and then sucking up the particles. They get sucked up through the spacecraft. They get caught by a little cup. We're getting there. Okay, so they get caught by a cup. As they come flying by, it fills up the cup with our sample, and then we can analyze that with the mass spectrometer, laser beams. It's much more interesting when it's not me narrating. The NASA guy had a nice script. But what we're looking for are compounds of prebiotic interest, like oleic acid, which we can discover with this technique. There's different ways of analyzing it. I'm not a chemist. I do not understand all the details of all these things. But one thing we're going to be looking for is called stereoisomers. This is really important in life. Life tends to use only one isomer and not the other. So if you find that all the molecules are only one isomer, that is a strong indication that you might have life present. For example, all of the amino acids in our proteins are left-handed, I believe it is, and all of the sugars in our carbohydrates are right-handed. And that's pretty weird because in the universe, you should find an equal mix of both-handedness, but we don't. So we're going to be looking for patterns like that to help us determine whether or not there's life on Titan. All right, so to summarize, I'm convinced that Dragonfly is going to revolutionize our understanding of prebiotic chemistry and the habitability of planets unlike the Earth. And now we just, like I said, now we have to go and collect the results. So onward to Titan. Thank you all for your attention. I'm happy to take any questions at this point. Yes, sir. We're going to give it commands to tell it where to go, but it cannot be real-time operations. The delay time between Earth and Titan is 2 hours. So we're going to have to feed it instructions, and then it will execute them at the appropriate time. Yeah. Yes. I don't think the sorry. Is the atmosphere's corrosiveness and temperature going to be a problem? I don't think the atmosphere should be too corrosive. There's no chemicals that I'm aware of that are terribly corrosive. I think we're safe there. In terms of temperature, we have this really hot nuclear generator stuck to the back of us. So we just use the waste heat to make sure the insides are all nice and toasty. So we should be okay there. Yeah. Yes. Yeah, it's like hundreds of kilometers away. Yeah, but yeah, it's you don't want to land on a crater's ejecta blanket. It's really rough and bumpy. That would be an unsafe place to land. So we want to make sure we're far enough away that we're landing somewhere safe, but not so far that it will take too long to get there. So we're trying to balance those two things. Yeah, in the back there. I'm sorry. Yeah. How does the extreme weather on Titan perhaps pose a problem for Dragonfly? Fortunately, the weather on Dragonfly is pretty chill. We're 10 times as far from the sun as the Earth is. So we don't have hurricanes and anything like that. Honestly, we've seen very little evidence for high winds on Titan. It rains maybe once a season at the equator where we're going. And so we're just going to avoid that time and just land at a different time when we're not expecting to see any clouds. However, if we do detect a freak storm, we just won't fly that day. We'll test, if it's raining, if it's too windy, we'll just wait till the next day and fly there, much like, aircraft pilots on Earth do, right? Yeah. Yes. Yes, you're absolutely right. So he's asking, would we have to design the blades differently on Titan compared to Earth because the atmosphere is different? Yes, they're actually shorter on Titan because it's easier to fly. So you don't need quite as big of a wing. So yes, we do need to consider that when we're making the flights on Earth, that we'll need a slightly different length of rotor than we would on Titan. Yeah, in the back. So the question is, what is Dragonfly's expected lifetime? I think our principal mission is a little over 3 years, 3 Earth years. But we're hoping that if everything is going well, that we'll continue on with an extended mission. Many NASA missions go well beyond their projected lifetimes, but that 3 years will hopefully get us to the crater where we can sample those materials. Yeah. Yep, in the back. Yep. So the question is, do we see evidence of plate tectonics? No, we see very little evidence of tectonics on Titan. Actually, we don't, and to be clear, we don't see plate tectonics anywhere else in the solar system other than Earth. We see limited tectonics on other planets. So there might be some going on, but it's not nearly as active as Earth is, primarily because it's colder out there. Yeah. Sure.
We've got someone who asks if you could tell us the launch date. You want to give us the sort of launch plan again?
Well, so that question is, what was the launch date? And honestly, this just keeps moving. We were really hoping for the 2027 launch date, but now that NASA has taken a bit of our budget away, it's been called into question. We're still working that out, unfortunately. I wish I had a more definite answer for you all. Yes. So the question is, why are the rotors stacked on each other? And I got to tell you, I don't know the answer to that question. I am by no means an engineer. Sorry. Yes. Right. Okay. So the question is, what about tides? There shouldn't be large tides on Titan. It is pretty far from Saturn. And so tidal forces are determined by a couple of things. One of them being the distance from their host planet, the other being the eccentricity of their orbit. So Titan is pretty far, its eccentricity is pretty low. So we think tides should be pretty minor on Titan, is my understanding. Yeah. Yes. So the question is, how does it get energy? It does not run on solar power. You do not get enough solar energy at Titan for that to work. Yeah. So we're bringing our own nuclear generator on board. This is the same thing that the Voyager mission had, and they're still operating like 50 years later. Curiosity and Perseverance also have a nuclear generator. Europa Clipper is going to have a nuclear generator. So it's a pretty common power source for that mission. In Idaho. The generator is going to be made in Idaho. Yep. The national labs. Excellent question. Yes. Right. So the question is about, how did I set up the experiment, and how does to make the amino acids, and how does that compare to the data we got from Voyager and Cassini? So I did try to make it close to what we thought Titan's atmosphere was. It was lower pressure, and it was at the temperature of dry ice, which is comparable to the temperatures we'd see in Titan's upper atmosphere. It's also a really annoying way to do an experiment because dry ice sublimates very quickly. So I'd be going into the university at 2 a.m. in the morning to dump more dry ice into this experiment because it took 5 days or so to make enough gunk. And so it's just days and days of topping up this dry ice to keep it cold enough to sort of mimic Titan's atmosphere. Yeah. Yes. So the question is, does Dragonfly come back, or does it stay there? No, it stays there. It's very rare to have something come back to Earth, and those are very expensive missions. So there's only been a handful of cases where that's been the case. And usually it's just a portion, like a capsule. It's not the whole spacecraft. But if you're interested, OSIRIS-REx, which is that other New Frontiers mission I was mentioning, is sending a piece of the asteroid Bennu back to Earth this fall. So that's one of the rare cases where something does come back to Earth. Yeah. Yes. Yeah, so that's a good question. How are there mountainous parts of Titan with no tectonic plates? There is some limited amount of tectonics. It's just not the plate tectonics that we see on Earth. There's a different mechanism for causing that. You can get, the whole planet can shrink, that can cause tectonism. Or tidal forces were mentioned. you know, there's other ways you can get a little bit of tectonics to make mountains, but the mountains there are very small. Titan is overall pretty flat compared to Earth. Yeah. Yeah. How many samples are we going to be able to collect? Ooh, we have something on the order of 30 cups, I think. I can't remember. It keeps going down. Shedding weight. Dragonfly was too heavy, so we're like ditching things left and right to make it lighter. So I don't know exactly the number, but it's on the order of like 30, I'd say. So that tells us how many samples that we can collect and analyze. So we have to be careful, right? We're not just going to be sampling every little outcrop we see. We have to really pick the site carefully. A lot of arguing with scientists. Yeah, probably is how it's going to turn out. All right. All right, last question. Yes, sir. Sure, is going to be successful. Gosh, I wish I could say 100%, but with spacecraft, there's always, I think it's better than 50-50. NASA is pretty conservative. Honestly, NASA has not had a major failure on one of its missions for a very long time. So I'm hopeful this is going to be successful. All right, my daughter is heckling me from the back of the room, so I think that's a good place to end it.
Yes. Well, thanks for coming out, everybody. If you're interested in seeing this girl, I'll invite you to stand out in the lobby and wait for us to take you upstairs. And thanks to everyone who showed up online. We appreciate it. Have a good weekend, and we'll see you in June.